Steam is the driving force in many power plants. It is used to run the turbine, to heat feed water, and to perform various other functions such as heat tracing pipes and powering auxiliary equipment. Separate steam systems direct and control the steam for specific applications. In this unit, we'll look at the typical components of several different steam systems, and we'll see what you need to do as an operator to make sure that the steam systems in your plant operate safely and efficiently. It takes several systems working together to generate the electricity that's produced in a modern power plant. The required systems include a boiler, a turbine, a condenser, a condensate and feedwater system, and several other steam systems. Altogether, these systems and their components make up a flow path that is referred to as a plant's steam-water cycle. In this part, we'll use simplified diagrams of a typical steam-water cycle to look at how steam flows through the various systems and components. However, you should be aware that the exact numbers and types of components and the ways in which the components are connected vary from plant to plant. We'll begin our review of the steam-water cycle at the boiler. The boiler uses heat from burning fuel to convert water into high-pressure, high-temperature steam. Steam produced in the boiler flows into the main steam system. The main steam system is a system of pipes and valves that directs and controls the flow of steam from the boiler to the turbine. The functions of the valves in the main steam system are covered in another part of this program. For now, our focus is strictly on the steam flow path. Steam entering the turbine flows through the nozzles and blades of the turbine and causes the turbine shaft to rotate. The mechanical energy of the rotating turbine shaft is converted into electrical energy by the generator. As steam flows through the turbine, a portion of the steam is extracted through a system of pipes and valves. This system is called the extraction steam system. The function of the extraction steam system is to direct the flow of extraction steam to the feedwater heaters. In turn, the feedwater heaters improve plant efficiency by using the latent heat in the extraction steam to heat feedwater. Simply put, latent heat is energy that when added to a substance or taken away from a substance causes a change in state, but not in temperature. The steam that isn't extracted by the extraction steam system is exhausted from the turbine into the condenser. The circulating water that flows through the condenser cools the exhaust steam and converts it into water that's called condensate. From the condenser, the condensate returns to the condensate and feedwater system, which consists of several pumps, heat exchangers, a feedwater storage tank, and various pipes and valves. This system directs and controls the flow of condensate from the condenser to the boiler. A condensate pump is the first component of the condensate and feedwater system. The pump is used to increase the pressure of the condensate and move it into condensate piping. The next components are two feedwater heaters. In our example, one heater is a U-tube shell and tube feedwater heater, and the other is a deaerating feedwater heater. That's usually just called a deaerator. As the condensate flows through these feedwater heaters, it is heated by extraction steam. The deaerator also removes air and non-condensable gases that may be in the feedwater. In this system, the deaerated feedwater is stored in a feedwater storage tank, sometimes called a deaerator storage tank. The water in the deaerator storage tank is used to supply the demands of the feedwater system. From the storage tank in our system, the water flows to a condensate booster pump. This pump increases the pressure of the feedwater and moves it through piping to the boiler feed pump. The boiler feed pump, sometimes called a feedwater pump, also increases the pressure of the feedwater. The additional increase in pressure moves the feedwater through components such as feedwater heaters, piping, and valves to the boiler. Finally, in the boiler, the steam-water cycle begins again. In this part, we'll see what the components of a main steam system are, and we'll look at the functions of each of these components. The main steam system controls and regulates the flow of high-temperature, high-pressure steam as it moves from the boiler to the turbine. Main steam piping is usually large, heavily insulated piping. It contains and directs the flow of steam from the boiler through the main steam system to the turbine. Safety valves are installed in the main steam piping to protect the system from damage due to overpressurization. We'll use this simplified diagram of a main steam system to take a closer look at how the components in the system work together. We'll begin with the safety valves. Although we show only one safety valve in our illustration, a main steam system usually contains several safety valves. If system pressure exceeds the setting of a safety valve, the valve opens quickly and vents enough steam to the atmosphere to relieve the excess pressure. Many main steam systems have boiler stop valves that can be closed to isolate the turbine from the boiler if the need arises for maintenance, troubleshooting, and the like. The boiler stop valve in this main steam system is a motor-operated valve. The next component in our main steam system is the main steam stop valve. It's usually a specially designed hydraulically operated valve. The valve operator is controlled by the turbine control system. Although we show only one main steam stop valve in our simplified diagram, there may be two or more of these valves in a main steam system. The main steam stop valve safeguards the turbine from overspeed and other potentially damaging conditions. During normal operation, the main steam stop valve is fully open. But if the flow of steam needs to be shut off for any reason, the valve quickly trips closed to stop steam flow. From the main steam stop valve, the steam flows into the steam chest. The steam chest is a collection area designed to distribute the steam to the hydraulically operated turbine control valves. A main steam system usually contains several turbine control valves. For simplicity, however, we show only two. Steam chests are sometimes contained in housings like the one shown here, with the turbine control valves located inside. The control valve actuators are above the steam chest housing. The actuators are controlled by the turbine control system. The positions of the turbine control valves determine the amount of steam that's allowed into the turbine. The valve positions are changed depending on the desired load. The valves are moved in the open direction so more steam flows into the turbine to increase turbine output. The valves are moved in the closed direction, which reduces the amount of steam that enters the turbine when it's necessary to decrease turbine output. They can also close completely to help protect the turbine from overspeed conditions. When the main steam flows through the high-pressure section of a turbine, a lot of the steam's energy is used to rotate the blades that are attached to the turbine rotor. To increase overall plant efficiency, many plants direct steam that has flowed through and been exhausted from the high-pressure section of the turbine into a reheat steam system. This steam system then increases the energy of the steam and returns the reheated steam for use in the intermediate pressure section of the turbine. As we've indicated, in a plant that has a reheat steam system, the turbine is generally divided into sections. The turbine in this simplified diagram, for example, is divided into three sections: a high-pressure, or HP section, an intermediate, or IP section, and a low-pressure, or LP section. The steam that's exhausted from the HP section of the turbine enters the cold reheat piping. Cold, of course, is a relative term. The exhausted steam is at a temperature of several hundred degrees Fahrenheit, but it's cold in comparison with its temperature later, when it will enter the hot reheat piping. The cold reheat piping directs the exhausted steam from the HP section of the turbine to the reheater section of the boiler. The reheater section of the boiler contains hot combustion gases. The hot gases increase the temperature of the steam to the desired value for efficient operation of the IP and the LP sections of the turbine. The reheated steam flows from the reheater section of the boiler into the hot reheat piping and is directed to the IP section of the turbine. There are several valves in the hot reheat piping. These valves typically include safety valves. reheat stop valves, and intercept valves. For simplicity, we've shown only one of each of these valves in our diagram. Usually, though, a reheat steam system has several of each of these types of valves. Let's take a closer look at the functions of the different valves in the system, starting with the safety valves. The function of a safety valve is to protect the system from excessive pressure. If the steam pressure in the hot reheat piping exceeds the setting of the safety valve, the valve will open quickly to vent the excess pressure and thus prevent damage. As we've said, reheat steam systems also include reheat stop valves and intercept valves. These are specially designed valves that are operated by hydraulic cylinder actuators that are controlled by the turbine control system. The functions of reheat stop valves and intercept valves are similar to those of the main steam stop valve and the control valve found in a main steam system. One of their chief functions is protecting the turbine from overspeed. Turbine overspeed occurs if a turbine shaft spins faster than its design speed. When this happens, the increase in rotational stresses on the turbine's parts could cause serious damage. We'll use this simplified diagram, which includes both the reheat steam system and the main steam system, to see how the reheat stop valve and the intercept valve, in conjunction with the turbine control valves and the main steam stop valve, work together to protect the turbine from overspeed damage. When turbine speed increases, the turbine control valves close. If the speed continues to increase, the intercept valve closes to reduce the flow of steam to all three sections of the turbine. If turbine speed still continues to increase, the main steam stop valve and the reheat stop valve trip closed completely, which stops the flow of steam to the turbine. As with any steam system, the piping is a critical component of a reheat steam system. Like most steam system piping, it's large, well-insulated piping that's designed to contain and direct the flow of steam. Of course, temperature changes will cause the piping material to expand or contract. So to handle these changes, the piping has expansion loops and bends that let the piping expand and contract without damage. In addition, pipe hangers and supports both support the piping and allow for some movement during expansion and contraction of the piping material. A large amount of the energy in the steam that's produced in a power plant is used to rotate the blades mounted on a turbine shaft. However, even after this is done, there's still a considerable amount of energy remaining in the steam. This energy is called latent heat. Simply put, latent heat is energy that when added to or taken away from a substance causes a change in state, but not in temperature. With an extraction steam system, the latent heat can be recovered or extracted from the steam that is passed through the turbine and can be used to heat the feed water that flows through the feed water heaters. This in turn improves overall plant efficiency. Simply put, an extraction steam system is a system of pipes and valves that directs the flow of extraction steam from the turbine to the feed water heaters. We'll use this simplified diagram of a typical extraction steam system to look at how the components in the system work together. In our example, there are 3 extraction steam lines, one from each section of the turbine. In an actual extraction steam system, however, there are usually more than 3 lines. Each extraction steam line contains an isolation valve and a non-return valve. Typically, the isolation valves are motor-operated gate valves, and they're usually open during normal operation. However, if a feed water heater needs to be shut down for any reason, the isolation valve is closed to stop the flow of extraction steam from the turbine to the feed water heater. The non-return valves protect the turbine from backflow if the flow of steam from the turbine stops. As shown in this simplified illustration, during normal operation, a non-return valve operates like a swing check valve. The flow of steam from the turbine keeps the valve disc open. But suppose backflow occurs, as can happen if the pressure in a turbine drops and water in a feed water heater begins flashing into steam. Then, as the volume of steam increases, steam will begin flowing back through the extraction steam piping and into the turbine. That could cause overspeed. But the non-return valve closes to prevent the backflow and protect the turbine. Many non-return valves have air assist actuators that are connected to the valve disc. The actuators automatically trip closed if the turbine trips. The non-return valves also protect the turbine from damage caused by the backflow of water if there is a high level in a feed water heater. As illustrated here, an air assist actuator is usually connected to a level controller that's located on the feed water heater, which in this case is the deaerator. The level controller monitors water level in the feed water heater and controls the air assist actuator on the non-return valve. If the water level in the feed water heater rises above the predetermined set point of the level controller, the controller sends a signal to the air assist actuator. The actuator then trips the non-return valve in the extraction steam line closed before backflow can reach the turbine. Low-pressure extraction steam lines in which steam pressure is less than atmospheric pressure may not have valves. Backflow and high heater level aren't of much concern in this situation because these conditions are unlikely to cause problems. In the case of backflow, the low-pressure steam usually passes through only the last few stages of the turbine and then exhausts into the condenser. Under these circumstances, there's not enough steam involved to overspeed the turbine. Likewise, high level is generally not a problem in low-pressure systems because water in the drains for the feed water heaters usually flows directly into the condenser. The drains are large enough to keep the water level from getting too high and to keep water from entering the turbine. Steam that's used for purposes other than driving a turbine or heating feed water is generally referred to as auxiliary steam. In this part, we'll see some typical uses of auxiliary steam in a power plant, and we'll look at the operation of the components that control the pressure and temperature of auxiliary steam. There are many different components that might use auxiliary steam during normal power plant operation. Plants that burn oil often use auxiliary steam in heaters to heat the oil and make it easier to pump. In addition, piping for transporting oil may be equipped with steam tracing lines. The auxiliary steam in these lines keeps the oil in the piping heated and flowing smoothly. Plants that burn oil or coal also produce soot. In many plants, soot blowers use auxiliary steam to remove soot from boiler tubes. In some plants, the makeup water purification systems include evaporators that use auxiliary steam to heat the water. Also, auxiliary steam is often used to power equipment such as turbine-driven boiler feed pumps. The auxiliary steam is supplied to the turbine, which operates like a main steam turbine, except that it drives a pump instead of a generator. In many plants, air ejectors use auxiliary steam to help maintain condenser vacuum. The jets of steam from the ejectors create a low pressure that is used to remove air from the condenser. As we've seen, there can be many uses for auxiliary steam in a plant. The exact source of this steam depends on the plant's design. But during normal operation, auxiliary steam is usually supplied by either the main steam system or the extraction steam system. In some cases, auxiliary boilers are used to supply auxiliary steam when a plant is shut down. Regardless of the specific design, though, most auxiliary steam systems have certain protective devices and control components in common, such as safety valves, pressure regulators, and temperature regulators. This is a simplified diagram of the control system for a typical auxiliary steam system. The control system can be divided into a pressure regulating branch and a temperature regulating branch. We'll look at the pressure regulating branch first. The components in this branch regulate the steam pressure in the auxiliary steam system. In our example, the pressure regulating branch of the control system contains two manual gate valves and a pneumatic diaphragm-operated control valve. The gate valves are isolation valves. They're open during normal operation, but they can be closed if necessary to isolate the branch from the steam supply source. The pneumatic diaphragm-operated control valve is a globe valve that is used to regulate pressure. The valve is connected to a pressure controller that monitors steam pressure in the downstream piping. If pressure decreases below the set point, the controller sends a signal to the valve operator to open the valve to allow an increase in steam flow with a corresponding increase in pressure. If pressure increases above the set point, the controller sends a signal to the valve operator to close the valve enough to decrease the flow of steam with a corresponding decrease in pressure. The valve operates as necessary to maintain pressure within the design range of the system. This line is the bypass line. In our example, the bypass line contains a globe-type bypass valve. During normal operating conditions, the bypass valve is closed. However, the bypass valve can be opened manually to allow steam to continue to flow to downstream equipment if the pressure regulator must be isolated for some reason, such as a leak or a malfunctioning control valve. The components of the temperature regulating branch of the control system are similar to those of the pressure regulating branch. However, the components in this branch regulate the flow of water to a de-superheater rather than the steam pressure that's supplied to the auxiliary steam system. For this reason, the valves and piping in the temperature regulating branch are usually smaller than the valves and piping in the pressure regulating branch. This simplified diagram shows the components of a typical temperature regulating branch. Our example has two isolation valves that are normally open, a pneumatic diaphragm-operated control valve for regulating flow, and a bypass line with a normally closed bypass valve. The water that flows through the temperature regulating branch may come from a separate water supply, or it could come from the condensate and feedwater system. The valves in the water supply line are used to control the flow of water to a de-superheater, which is represented on our diagram by this symbol. The de-superheater, also called a spray-attemperator, is a device that reduces the temperature of steam by spraying a mist of water into the steam piping. In our example, the flow control valve is connected to a temperature controller that monitors the temperature of the steam in the downstream piping. If the temperature of the steam increases above the designated set point, the temperature controller sends a signal to the valve operator to open the valve wider and allow more water to be sprayed into the piping, resulting in a corresponding decrease in steam temperature. On the other hand, if steam temperature decreases below the set point, the controller sends a signal to the valve operator to partially close the control valve to reduce the flow of water, resulting in a corresponding increase in steam temperature. During normal operation of the auxiliary steam system, both pressure and temperature are controlled automatically. In addition, most auxiliary steam systems include safety valves to protect the system from excessive pressure. In this topic, we looked at the components in a power plant's various steam systems. We examined the steam-water cycle, the main steam system, the reheat steam system, the extraction steam system, and the auxiliary steam system. Now try answering some practice questions on this material. When a plant is shut down, the piping and components cool and condensate can accumulate in the steam systems. To avoid damage when the plant starts up again, the condensate must be removed from the steam lines, and the steam systems and components must be warmed up gradually according to specific procedures. Startup procedures vary from plant to plant due to differences in plant design. In this part, we'll look at some basic startup procedures that can be used in most power plants. To show typical water and steam flows during startup, we'll use this simplified diagram of a main steam system. The system includes drain lines, a steam trap line, a steam trap bypass line, a motor-operated boiler stop valve, a hydraulically operated main steam stop valve, a main steam stop bypass valve, and a steam chest, with hydraulically operated turbine control valves. During plant startup, when a steam system is being returned to service, the valves in the system must be properly positioned for each stage of the startup process. The drain valves begin in the open position, since the drains for removing accumulated condensate from steam systems usually remain open during the entire period that a plant is shut down. The turbine control valves, the main steam stop valve, and the main steam stop bypass valve are closed. The boiler stop valve is opened. After the boiler is fired, steam begins flowing through the main steam system. Some of the steam flowing into the relatively cold system condenses almost immediately. and its heat is transferred to the piping and components. The condensate that initially forms in the cold piping flows out the drains. When the system has been sufficiently heated, steam begins blowing out of the drains. Then the drains may be partially closed. The main steam stop valves remain closed to prevent steam from entering the turbine. You see, before steam can be allowed to enter the turbine, several preliminary steps must be accomplished to prepare the turbine for startup. One important preparation is draining the turbine casing. When a turbine is shut down, condensate collects inside the turbine casing or shell. Before turbine startup, the drains must be opened to remove all of the condensate from the shell of the turbine. Then, when the condensate has drained, the drain valves can be partially closed. Another task that must be performed to prepare the turbine for startup is starting the circulating water system. The circulating water pumps move water through the condenser tubes to prepare the condenser for operation. Many turbines also use gland seal or sealing steam systems. For these turbines, starting the sealing steam system is a necessary part of startup preparations. The sealing steam system supplies auxiliary steam to the turbine gland seals. When the sealing steam valves are opened, steam enters the turbine gland packing to seal the turbine and prevent air from leaking into the turbine casing or steam from leaking out. Once the sealing steam system has been started, the sealing steam pressure must be monitored to ensure that it's in the correct range. One more step that needs to be accomplished before steam is allowed to enter the turbine is starting the air removal equipment. When the equipment has removed the air from the condenser in the turbine, a partial vacuum is created in the condenser. Now the turbine is almost ready to receive steam. However, there's one more step that must be taken. It involves the turning gear. When a turbine is shut down, the turbine rotor is placed on a turning gear, which is a motor and gear arrangement that keeps the rotor turning at a constant speed. This is done to maintain uniform cooling of the rotor and prevent it from bowing or warping. The rotor then remains on the turning gear until steam is allowed to enter the turbine. Be aware, however, that turbines that have been shut down for an extended period of time may not be turning on the turning gear. In that case, you must place the turbine on the turning gear for a specified amount of time before you proceed with turbine startup procedures. With the turbine on turning gear, the shaft speed and eccentricity are monitored to determine if the turbine rotor is bowed. The bearing temperatures and lubrication are also checked. The lubricating oil is checked for foaming, and abnormal color or other unusual characteristics that may indicate there's a problem that could severely damage the bearings. Admitting steam to the turbine is the first step in a turbine startup. After the turbine has been reset and a speed has been selected, all of the valves on the turbine will open, except for the main steam stop valves. Electrohydraulic servo valves operate internal main steam stop bypass valves to control the rate at which steam is admitted to the turbine. The entering steam increases the speed of the turbine until the shaft rolls off the turning gear. Then the turbine valves are closed so that the turbine can spin freely while an inspection is performed. The turbine control instruments are checked for unusual readings, and the turbine is inspected for any unusual characteristics such as abnormal noise, excessive vibration, or unacceptable lubrication temperatures. If conditions are normal, the main steam stop bypass valves can be reopened, and shaft speed can be increased at the rate prescribed by plant procedures until the shaft is turning at rated speed. Now the generator can be prepared for startup. As soon as the generator has been synchronized or tied online with the electrical distribution system, the load on the unit is increased. Then the drains in the steam systems are closed according to plant procedures. Once the unit is at normal operating conditions, startup is complete. As an operator, it's your responsibility to inspect the various steam systems in your plant to ensure that they continue to operate safely and efficiently. In this part, we'll look at some typical routine checks that you should make, starting with checking for leaks. Even though a steam system may be well constructed, leaks can occur in valves and pipes. Leaks in valves often occur through the packing. Common symptoms of this type of leak include visible vapor leaking around the stem of the valve, dripping water, or the hissing sound of escaping steam. Steam leaks can be dangerous. Report them to a supervisor and warn plant personnel about the hazard. Whenever you're inspecting a steam system, check the pipe hangers and supports. Make sure that they're in good condition, not broken or damaged. When heat escapes from steam piping, some steam may condense inside the piping. Steam traps are located at low points in steam lines where condensate naturally collects. As illustrated here, a steam trap removes accumulated condensate without allowing steam to escape. Steam traps should be checked periodically to make sure that they're operating as they should. Some steam traps have test connections. Generally, if a trap is operating properly, only a relatively small amount of condensate will leave the trap line when the test connection is open. Then steam will begin to flow out. Another important check is to inspect the non-return valves in the extraction steam system. You can visually check the position of a non-return valve. During normal operation, the valve should be open. However, a non-return valve's disc should be able to move freely so the valve can close when necessary. In some cases, you may be able to push up on the valve's operating arm to make sure that the disc is free to move. Some non-return valves have air assist actuators to help ensure closing. You'll need to check the air assist actuators to be certain that they're operating properly. To do this, operate the controls that move the actuator and observe whether the operating arm is free to move. Finally, during routine inspections, you should double-check that the valves on all the steam systems are correctly positioned or lined up. You should also monitor steam pressures and temperatures to make sure that the various steam systems in your plant are functioning properly. Different systems operate at different pressures and temperatures, so you have to know the normal operating temperature and pressure for each system. In this topic, we looked at some basic procedures for removing accumulated condensate and gradually warming up steam systems during a plant startup. We also saw some basic inspections that operators need to make to ensure that steam systems are operating properly. Now try answering some practice questions on this material.